Okay, so we talked about wholes, which we'll call the removable discontinuities. So now we're going to focus on what happens at those vertical asymptotes from that graph that we previously looked at. So this says, based on your knowledge from pre-calculus, we know that if a rational function has a non-removable infinite discontinuity, graphically that's going to be talking about the vertical asymptote. So a vertical asymptote exists. So since the y values do not approach one specific value from both sides out of a vertical asymptote, so just like on the last example, so remember here, when we had a vertical asymptote, one side approached infinity and one side approached negative infinity, not real numbers. But it says, then the limit does not exist. However, we can determine the one-sided limits and what they approach. They're either going to approach negative infinity or positive infinity. So it asks you just for the limit as x approaches 1. That doesn't exist if there's a vertical asymptote. But if it asks you one from the left or one from the right, you can figure out if it's going to be positive or negative infinity. So there's a way for us to do this. We're going to take all the different approaches and kind of combine them together. So, for example 2, it says, for each limit below, determine the sign of the simplified function to the right or the left. So, this is the same problem that we've been looking at this whole time. So when we factored this previously, we factored this as x plus 1 times x plus 3 over x plus 3 times x minus 1. And remember, we crossed out the x plus 3's, those were the removable points, which was a whole. But this x minus 1 is still left over in the denominator, and that's a place where it's not continuous. And if it's left over in the denominator, that means it's a vertical asymptote. And that's what we call the non-removable because we didn't cross it out. So what this is saying, if I ask you the limit as x approaches 1 of f of x, that's not going to exist because there's a vertical asymptote there. One side's going to infinity, one side's going to negative infinity. They're not both going to a real number. So remember that limit doesn't exist. Okay, so how do we figure out though the left and right sided limit? So this asks us for the limit as x approaches 1 from the left here. So what we're going to do is you're going to take the simplified fraction. Now the simplified fraction up here is what you have after you've canceled out. So x plus 1 over x minus 1. And if we're trying to find the left side, you're going to plug in a number to the left of x equals 1, which means a smaller number. Now you do want to get a smaller number that's very close to the number. So if it's 1, you want to pick something like 0.9 or 0.95. It's got to be close. If you get too far away, then there could be other stuff happening in the graph that's going to mess up your answer. So you're going to plug in that number that you picked. So they picked 0.9 for it. So we're going to plug in 0.9 at the simplified fraction. So 0.9 plus 1 over 0.9 minus 1. Now we do not care what the actual numbers are. We just care if it's positive or negative. Because remember, the answer has to either be positive infinity or negative infinity. So 0.9 plus 1 is going to give me a positive value, and 0.9 minus 1 is going to give me a negative value. Well, if I have a positive over a negative, that's going to be negative. So what this tells me is the limit as x approaches 1 from the left of our f of x is going to be negative infinity. Okay, because your answer is going towards a negative number, that means that on your graph here, if it's going towards negative numbers, it would have to be getting smaller and smaller, so negative infinity. So then when you do the right side, the limit as x approaches 1 from the right, we're doing the same thing. So you're going to pick a number that's to the right, so it would be a bigger number. So pick a number to the right of x equals 1, so a bigger number. But you still want to make sure the number is very close to that number so that nothing else is going on in your graph. So I'm going to pick 1.1. We're going to plug it into our simplified fraction after we had canceled. And remember, we do not care about the actual answer, we just care about positive or negative. So 1.1 plus 1 is positive, 1.1 minus 1 is positive. So this is going to give us positive answer. So this tells us the limit as x approaches 1 from the right is going to be going towards positive infinity. Okay, so this gets a little confusing to people, but anytime you have a vertical asymptote, algebraically a vertical asymptote is what's left in the denominator after you cancel. If there's a vertical asymptote and it asks for the limit as x approaches that number, that specific number that it's going to be, it's not going to exist. But if they ask you for the limit going from the left or from the right, you can figure that out. The answer is either going to be positive infinity or negative infinity. You're going to pick a number either smaller or larger, but very close to the number. Plug it into the simplified version. It only matters if it's positive or negative, and whichever one it is, that's going to be either negative infinity or positive infinity. Okay, so that's for the vertical asymptotes. Wholes, remember we just factored, and then we got to plug in. All right, another type, for example 3, is when we have square roots involved. So it's going to be called a technique called rationalization. And you should have heard this before at some point, but we're going to use it for a limit. So just to look at this, the limit as x approaches 3, they gave us the graph that goes with it. So if you come in from the left and you come in from the right, we do get a y value. So there is an answer. It looks like it could be like, I don't know, it's a little less than 1/2, so somewhere around there. So we're always going to try direct substitution first. So I'm going to go ahead and plug in that 3 and try direct substitution, because you never know. Well, I end up with, we're going to end up with just 0 in the denominator, so we go on top. Regardless, this does not work. Okay, so if you can't do direct substitution, the next thing that we said that we could do would be factor. Well, we can't factor some square root, so factoring's out. So if you can't factor, what you're going to do is you're going to rationalize. And what that means is you're going to take this fraction here. Okay, so we're going to have the square root of x plus 1 minus 2 over x minus 3. Rationalize means you're going to multiply by, it's called the conjugate of the one with the square root. So you're going to write this exact same thing, except for you're going to change this to the opposite sign, so plus. So we're going to have the square root of x plus 1 plus 2. And if you put it in the numerator, you have to also put it in the denominator, because that's like multiplying by 1. So we're not really changing the problem. Okay, so here we go. We're going to multiply this out. So the square root of x plus 1 times the square root of x plus 1. The square roots will cancel and we'll just get x plus 1. Okay. Then the square root of x plus 1 times 2. That would just be plus 2 square root of x plus 1. Then we have negative 2 times the square root of x plus 1. That's negative 2 square root of x plus 1. And then we have negative 2 times 2, which would be negative 4. That's what my numerator looks like. For my denominator, you are not going to multiply anything. You're going to put everything in parentheses. So I'm going to put x minus 3 in parentheses, and then the square root of x plus 1 plus 2 in parentheses. Do not multiply out the denominator. In the numerator, your middle term should always cancel. If they don't cancel, then you messed up. So these two should cancel, and they do. So we are left with, so as x plus 1 minus 4, well, that's x minus 3. And then we have this stuff in the denominator. Now, the whole purpose of rationalizing is so that something cancels. If it doesn't cancel, then you messed up again. So keep those things in mind. It'll help you so that you stay on the track. So we have this x minus 3 that cancels. So I'm left with 1 over the square root of x plus 1 plus 2. So now that we've rationalized, think about this as like factoring, but we're rationalizing because we have a square root. Now we can find the limit. And we're finding the limit as x approaches 3. Well, now that we've made our limit into something like this, now we can use direct substitution. And we're going to just plug in that 3. So we're going to end up with 1 over 4, which makes sense. That looks about like 1/4 for our graph there, and that's where that y value is. So rationalizing the technique, so when we did factoring earlier, we did the same thing. We factored, we made our simple fraction, then we did a direct substitution. Here we are rationalizing because you have the square root. We got rid of our x minus 3, which was the problem. Then we can do direct substitution and you can plug it in.